Okay, hopefully this means you have finished all of your Ohm's Law lab work and are ready to go into how we're going to apply this in class. So, you determined Ohm's Law in your lab. You should have gotten that V is equal to IR, which is our big equation. Keep in mind for this, V stands for voltage. The units are volts. And the big takeaway from this is that if you're talking about the total current or the total related to the circuit, you're going to use the battery voltage. However, if you're talking about an individual resistor, this voltage applies to the voltage just across that one resistor and not necessarily the battery voltage. I is still current, it's measured in amperes, and R is resistance, which is measured in ohms. Now, once we've applied Ohm's law, we can find the current or whatever, and then we can talk about the power that we're going to get. And power, if you remember, is the rate of energy transfer per time. And in this case, we're going to be converting our electric potential energy, the voltage, the stored energy from the batteries, into electrical current energy, or moving energy and actually powering something in a current. So remember, power is energy per time. We also know that voltage was our electric potential energy per charge. Well, we also know that we're converting potential or stored energy into current or moving energy. And remember, our current is basically charge per time. So if we want to get energy over time, what we'll end up having to do is say that power is equal to the current, charge over time, times the voltage, energy per charge. Okay. So this is our big equation. Again, power, P, capital P, is measured in watts, and current, I, is measured in amperes or amps, and V is the voltage and is measured in volts, also a V. So, to work on this, what we're going to do is look at a new question that you should have in your packet. We have a total of 6 resistors arranged as you see here. What we're going to be doing with all of this is figuring out some of the types of questions the way I'd ask them in a test or something like that. So, and in this case, we're told in the problem statement that the battery voltage is 3.20 volts. So our first question is to determine the equivalent resistance. So in determining our equivalent resistance, what we're going to do is identify our 2 parallel combinations to start so that we can rearrange it and combine resistor 2 and 3 in parallel, which will give us a total of 66.7 ohms. And we're also going to combine resistors 5 and 6, which are also in parallel, and that combination will give us a resistance of 75 ohms. Then we now have resistors 1, 2, 3, 4, and 5, 6, which are combined in series. So combining those in series into a single REQ means we can just simply add them together, which will give us a total resistance that is rounded to 392 ohms. Okay. The next question in our packet is, now that we know the equivalent resistance, determine the total current coming from the battery. To get the total current, we're going to need to use our V is equal to IR. Simple enough, that's our Ohm's law equation. So this time, since we want the total, we're going to use the battery voltage for this, but and we're looking for the current, so we're going to do our isolation and get that I is V over R. So when plugging in our numbers, we're going to want our total battery voltage, which is 3.20, and our total equivalent resistance, because we're looking for the total here. So that would be the 391.666 repeating, which gives us an answer of 0.00817012, on and on, which rounds to a current of 8.17 times 10 to the negative third amperes, or 8.17 milliamps. Good to go. Now that we know the current, we can easily find how much power this circuit generates. And the power is a very straightforward calculation. Power is I times V. We know the current, and we know the voltage because we're looking for the total power, and plug that in our calculator, and we check out that the total power is 0.0261 watts. Thank you.